Last week, we looked at RAG, Retrieval-Augmented Generation. I'm just going to do a very quick recap. And after that, we'll continue with the RAG because we had not finished. As of last week, we looked at what RAG is and the fact that it basically combines information retrieval with large language models. But of course, the pipeline requires before you can retrieve information, you have to ingest it first. So you have an ingestion pipeline, then a retrieval pipeline, then an augmentation pipeline, then a generation by the large language model. And you can see it here. The ingestion pipeline has the documents, you chunk the documents. First of all, you load the documents, and then you chunk the documents and then you embed the documents. So we've already talked about embeddings and what embeddings are. Then those embeddings are metadata around the document. You store them in a vector database. That is the ingestion phase. You do that whenever a document is uploaded. Maybe you are writing an endpoint or something, right? Or just an application. When people upload documents at the point of upload, that's when you do the ingestion. Then you now have the second phase, which is the retrieval. When somebody is um, interacting with your application and is trying to retrieve information or query the large language model or the agent, the person will type a prompt. You then use that prompt, you embed it, and then when you embed the prompt, you get the equivalent vector embeddings for that prompt, which represents the meaning. And then you use that to search for context, content in the vector database that is similar in meaning to that. And then you use that to form context for your model. So those are the things, those are the things that you do, right? When you are um, in the retrieval phase. And then when you retrieve the information, you prompt, you use it to boost, right, the prompt that you send to the large language model so that it can give you an answer. Right. And this is the process for the ingestion pipeline. Like I said, you have the raw documents, you have the loading of the documents, you have to clean the documents sometimes, you have to chunk them because documents are typically very large. So you have to split them into smaller, manageable sizes. And then embedding is when you use an embedding model to generate the corresponding equivalent vector that matches, that chunk or the various chunks, and then you store it in the vector database, which is what I've just gone through. The types of documents, all kinds of documents, basically. And so we've gone through all of this. I'm just kind of doing a recap. You chunk because of size. You want to reduce them to manageable, small sizes that can be green, you know, it, so we also talked about embeddings. And we talked about um, the fact that embeddings are numerical representations of meaning. And the meaning can be in any domain or any modality, text, images, speech, whatever, recordings, okay? And it's semantic, so it has to do with meaning. We looked at embeddings, the fact that how embeddings represent meaning. And we also looked at the fact that when you want to compare embeddings between two different embeddings, right? Embeddings of two different things, we typically use a similarity search. And we also mentioned the different kinds of similarity search that we have. We have a cosine similarity search, we have the Euclidean similarity search, and then you have the dot product. So those are the three that are currently available and being used. And they are essentially based on the same principle of calculating the distance between 2 points in a multi-dimensional space. So the cosine similarity uses the angular distance between a vector line that's drawn from the origin in that multi-dimensional space to each of those points, right? That the meaning or the embedding represents, while the Euclidean distance is measuring not the angular distance, but the linear distance between the 2 points. So, yeah, and that's all of that. Then you can create embeddings the same way you can call a model to generate text. It does exactly, it's the same way, right? The only thing is that for most SDKs, they'll have a special embeddings uh, package, right, that you would call rather than the models sub package. So we saw how we can do this with OpenAI type of client. And then we also saw how we could do this with the Hugging Face sentence transformers. And what you always get back is that list of numbers. We also looked at vector databases. There are so many different types. You have the cloud-based ones, and then you have the ones you can install locally on premise. And then you even have the ones that are not really databases, but are libraries that help you to do the vector search, similarity search in an efficient way. So we have Chroma. Chroma is on cloud, but you can also install it locally. We have FAIS. FAIS is not really a database per se, but it is more of a library that gives you that capability. And then we have Milvus, we have Quadrant. Then we have the managed services, the cloud-based ones, Pinecone, Weaviate, MongoDB, Elastic. And we used Pinecone when we did some of the examples. And this is how you can access them. Um, you have to check documentation for some of these SDKs since each of them do things differently. So effectively, for you to build a RAG, you would first of all have to build your ingestion pipeline, chunking data, generating embeddings, storing in the vector DB, in the vector database. And then you now come to the retrieval part of it where the user asks a question. You then use the user's query to generate a vector and then use that vector embedding to search for the nearest matches using similarity search. And then once you do that, um, then you can retrieve the top K matches based on similarity search and feed that as context to the large language model, in addition to the original query, just like what we did when we were doing prompt chaining. And then the large language model is able to use the additional information to give you or to give your user a useful answer. Yeah. So we are going to do quick, naive RAG with JavaScript, just to ensure we see how we can do the same thing from both ends. So to do with JavaScript, I have already opened up a code space. I'm just going to use this code space. Now, um, Okay, I'm going to switch to VS Code because it seems the code space is a bit slow due to the weak network. So I'll switch to VS Code. So we are just going to work on VS Code terminal. I'm using the terminal and then using the terminal along with the we'll just uh, do a very basic JavaScript here. And I will also use VS Code for the LangChain part of it. So let's just start with a very simple, just a single file is enough for you to do a RAG, and I will try it out. Naive rag dot ts. I'll use TypeScript. So the same thing we have been doing. We are going to start off with um s- first thing is we start with ingestion. So we're not going to load documents here. We'll just take a simple text file. Okay, so it starts with a simple text file. So loading a simple text file, we can use a file system module in Node.js. So we'll create a function. Um, I think we can just read directly. Import fs from fs. Okay. Then let's also handle paths. Then .m um for handling the environment variables, which I already have a couple of them here. Okay. So the first thing is for us to load a file. Let's create a simple document, simple text file here. Um, we could, and I'm going to get com com uh, some content that I will put in there. Maybe the same thing I got last time, which was the from the artificial intelligence Wikipedia page. So we'll just get it from there. It's not very clean. Again, this is one other reason why we talk about cleaning content. So if you are doing a full retrieval workflow, you have to remember that sometimes you need to clean the content. But for now, I'm just going to dump this here. So this was taken from the AI Wikipedia page, and I just dump it in here. Now, so we can then do a simple um, retrieval, sorry, simple chunking algorithm that is based on sentence-based chunking, basically, that does not, it's not very fancy. It's just going to split at the point of where you have um, either a period. So we would have a pattern, a sentence, we can call it sentence pattern, um, which is really just or delimiter pattern, the delimiter rejects, let's call it that. So this is just if it has this and then it has at least one space, one white space. So this can be a very simple pattern to use. We're not going to do anything fancy, but all of these other text splitters, they do a bit more interesting stuff. So yeah, load environment variables you call .env. Then to now split text from a file into sentences, okay? So you can see this, how this is done is it takes the file path of the file, then it reads the file synchronously, and then it just does a simple split using this, and then trim. So we are not using any chunking here. We could also do a more advanced chunking, like what we did when we were doing the Python one, right? Where you would uh, chunk and then um, try to specify the chunk size. One thing we could do is if you split the entire text into sentences, you're going to end up with a lot of sentences. And if you want to use a paragraph-based chunking, then you could do something like just splitting into sentences is not good for ingestion or for retrieval because you're only going to have one sentence. So you need to um, yeah, chunks. Um, let's call it paragraph chunking. So let's make a function that does that. And if you get the text or file path, we can still do that with the file path. Chunk size. We're not going to do overlap again, even though overlap is a good idea, right? But we don't have enough time to do it here. So in this case, we are going to read and split. Then we will now essentially loop through each sentence and continue to pad into a chunk until the sentence exceeds the chunk size. Then you move to the next chunk. So that's typically like the method that we do. And that's what we did the last time. Except this time we have split all the sentences rather than splitting it um, as we go. That would have been maybe a more efficient method, but this is naive, so we're not trying to optimize too much at this point. So, um, right. So what we do is we are supposed to check first if the current chunk um, okay. So we're trying to check. So what we do here is to um if the if the current chunk if so the current chunk is essentially a single it's a list of the sentences that you want to put into one chunk. You have not yet joined the sentences, so you are just putting the sentences into a stack, if you may call it that. So while you are doing that, you want to confirm several things that if you join all of the sentences in that chunk together, right? Plus the length of the next sentence that you want to add, plus one because of the extra space that you also have in between, right? That should not be greater than the chunk size. If it is greater than the chunk size, then it means that we cannot add any more sentences into that chunk. So we would then take the current chunk and put it into the chunks. But before we put it into the chunks, we have to join the sentences back because a chunk should be a single string of text, not a list of strings. So, but doing the list of strings just to help us manipulate that, do that manipulation. So that's what's really going on here. We are basically just adding sentences into the current chunk. And before we add the sentence into a chunk, we first of all check if the chunk is already full or if the chunk will be full or will overflow. That is to go beyond the chunk size if we add the current sentence. That's what this check does. So if the current chunk is going to overflow, then we don't add the current sentence, right? We rather join the sentences in that chunk together into a single paragraph or a single chunk or a single string, and then push that single string into the chunks that we have. Then we reinitialize the temporary chunk holder or current chunk holder. So that's a first step you always do when you are doing this kind of paragraph chunking. Then, but if this check is false, that means that the current chunk still has space for you to add the current sentence. So you just add the current sentence, right? And we don't need this anymore. And we just keep going that way until all the sentences are added. But at the tail end, there will still be probably a few sentences, a last chunk, because this condition here only happens when you want to add a sentence. But when you have finished all the sentences, you will have a particular current chunk that probably hasn't yet overflowed. So we have to deal with that as well, right? So we do that by just checking if there is a leftover, if there are leftover sentences, right? Right. And then if there are, you will join those and add into the chunk. And it's as simple as that. So that um, that completes the chunking, the simple sentence chunking script that we or function that we have here. So we've done simple paragraph chunking. Okay. Um, right. We should return. Yeah, forgot about that. There should be a return here, which is should return all the chunks that you have accumulated. Right. And after that, that's the first thing, paragraph chunking. After the paragraph chunking, then what you do is the next step would be embedding, right? I didn't talk about loading, but we'll talk about loading when we get to that point. So loading would really matter. We are already doing loading anyway. It's just that the loading here was very straightforward, simple loading. This is a loading. This read and split text. We are loading the file, right? And we're just using very basic read file sync to do loading. And the reason why this works is because it's UTF-8, which is text. So simple text, easy to load. But now think about if we had something that is not simple text, maybe an image, maybe a PDF, maybe audio file, maybe a PowerPoint document, something that is complicated, then loading it will not be as simple as this single line, right? It will be a bit more involved. So we'll come to talk about that later. So when you load, you chunk, you embed. Okay, maybe I should mark it that way. So this function does load the document. This function does chunking the document, chunk the document. Okay. Then we will have embedding the document. So embedding the chunks. So embedding, you have to then use one of these tools. So we will use the Hugging Face sentence transformer like we did last time. And we'll use the all mini LM. So it's not it's pretty easy to use a sentence transformer, but we're not going to download it. We're not going to use because if we use a sentence transformer, remember it's going to download. So we are going to use Hugging Face chat inference package, which we'll call an API. So um, all right. Um, or inference API. Let me not because their inference API is a more generic API, not just for chat. Okay. So of course, for this, we will need to install the Hugging Face Hub, right? Um, we need to install the Hugging Face Hub. To install the Hugging Face, uh, let's do that first here. We will run pnpm install Hugging Face at Hugging Face / inference. Okay. So once we install it, it's going to provide us their inference client, which we can import from here. Okay. Um, okay. Okay, so I think I had also lost .m in that process. So and OpenAI, so I'm going to reinstall those. All right, so yeah, because it created a new package JSON and therefore remove those other ones. Okay, so we will now go ahead to implement we'll implement our embedding. So embed chunks. I'll go with that. And the chunks, then you have a promise. So why this has to be an array, a two-dimensional array of numbers, is because remember we are embedding vectors. So the vector first is an array first of all, and then each chunk is going to generate one vector. So if each chunk generates one vector, that means each chunk is effectively um, an an array of numbers. So an array of those chunks will give us an array of numbers. So it's a two-dimensional array basically. Um, right now we create a new inference client. We can create the new inference client outside, or we can create it inside. I don't want to keep creating a new inference client each time, so I will create it outside the method. The only problem is if, yeah, so API key, um, so the access token has to be this. Um, yeah, I would say, okay, this is okay, I guess. Okay, so create new inference clients and we pass this in. I've not yet, uh, we'll figure out the TypeScript things yet later on. Okay, um, so to now embed, you really don't need to loop through because Hugging Face allows you to pass in the entire thing. Okay, so you can just, um, in fact, you could even pass in just an entire string. So let's put this in a loop. Now, response is client. Okay, client feature extraction. And then, so last time the model we used was sentence transformers or mini L6v2. So we'll still stick to that. And then we specify the inputs. So when you are doing feature extraction, you have to pass the model, you have to pass um, the chunks, which should be the inputs. And that is the minimum that you would pass. That should actually be sufficient. That should be sufficient for you to get what you need. So let me just double check that. So you run that and then you in okay, you get the response. The response will contain the embeddings. So you can then return the response. Well, this is a good suggestion. If the response is an array, right, you return that. Um, but if not, then you return a list. I'm going to double check this when we are running it. For now, I'll just leave it as it is. So, catch error. If you have an error, then you can just console log and maybe throw an error or something, you know. So that's the embedding part of it. Because of this type inconsistencies, I'm actually going to check it. I'm going to do manual checking when we're running it, and we'll tweak and fix whatever issues. I'm seeing a type inconsistency here, another one here. But let's continue. When we want to run it, we'll troubleshoot. Okay, so we now have the embed chunks that uses the Hugging Face inference client. I'm going to change this to HF API key, which is what HF token. I think what I have is HF. Okay, I don't even have that here. Okay, so HF, um, let's just call it HF token. I'll put that in there later on. So that's the second step, embedding. So always remember the steps. First one is loading document. Second is chunking. Third is embedding. Then the fourth is storage, right? Is So let me just mark that here. Step 4 is storage in the vector database. So for this, we will use Pinecone like we did last time. And Pinecone also has a JavaScript interface, just like it has for Python. You can actually check their website and you'll see all the documentation there. So they have a Node.js SDK. And for you to access that, you have to just install Pinecone and you'll be able to have access to the JavaScript. So you start first by installing, uh, this is what you install. It's called Pinecone database, according to their latest documentation. So you have it as pnpm install Pinecone database, Pinecone. So that will give you Pinecone. And then once you have their SDK, you just import Pinecone and then you can use it as usual. So let's go and import it here. We will import Pinecone from Pinecone database Pinecone, which is what we had here. Okay. Now, you can also create the instance of the Pinecone right here. You're not going to, you create an instance of the Pinecone client, which you can call Pinecone or PC or whatever you want to call it. And as usual, just like what we did with the Hugging Face, you specify API key. In their own case, what they're asking for is API key, not access token. So I'll also create this later on. Okay, so when you have a Pinecone database, the next thing you would want to do is to create an index. You have to create an index. or you can just get an index. So in this case, we already had an index, right? Which we used for the Python example that we did before. So I'm going to essentially just reuse that same index. So I know you will not see my browser now, but if you go to Pinecone, I'm opening my account. So we already had the um the index we created. Interestingly, Pinecone allows you to view all the indexes. So um so Pinecone, um you can use list indexes, for example. That would give you all the indexes. So one of the things we could do is just to console log it, right? And that allows you to see. The other thing is I can just get the first index. I think I have a bunch of other indexes. So I'll run this first so that I can have an idea of my indexes. This is something we can actually do right now. If I run, let's hope that we don't have errors. We might likely have errors, but let's see. So if I run node and nav rag, I need to change my node version. Um, I, so I'm going to run the node version 24 needs to be installed for me to use node on a TypeScript file. So I'm going to do that in the background. All right. So while that is going on, we'll build the function store embeddings. Yeah. So we have the embeddings and we have the index name. So of course we'll get the index. So use pinecone.index to get the index name. And then we now need to take this index, the embeddings, and map it into a shape, right? That works. So Pinecone, if you remember what we did last time, Pinecone will take IDs and values, and then there's metadata, which you can then put anything, particularly maybe the source, the content, right? So I'm going to put the content as well in my metadata. So the thing is, yeah, so I have to put the chunks as well. So I'm going to take the chunks and put them along with um the vectors. Okay. And then once I do that, then you can um again the typing differences. I'll work those out later on. Then catch error. We can just console log the error. And we're not doing anything fancy. So those are the steps. We store the embedding in the database. Um, and that's it. So now, after that, the next thing is retrieval. Okay. So retrieval. In retrieval, you start off with um, embed. Well, we already have an embedding method which we will reuse. We'll reuse this embedding method to embed whatever you know um, sentence or query that the user passing. We'll just pass it in as a single um, chunk, right? A string, a single array, right? So that means we can reuse this. And so we're going to get a single embedding. So we don't need another embedding method. We just use that. So then what we need to do is the retrieval. So retrieval means we have to do a search in the pinecone, right? So we get the pinecone, the index again, based on the index name, and then we can then run a query, right? We can run a query, and then we pass in the query options. So the query options, in the Python version, we're using query namespaces. And I was a bit kind of, because I'm not used to using query namespaces, I'm used to using query, right? So, but anyway, in this case, it will query everywhere without checking the namespaces. Okay, so we'll run the query, get a query response. Then when you get the query response, then you can find the matches. The matches will give you the top K matches. And again, we can catch any errors, log the errors, and that's all. I'm not going to worry too much about fancy error handling. So we have all okay, the last bit of it, after retrieval, the next thing is the um, the augmentation, right, and generation, where you will then take the you then take the retrieve chunks and the query from the user, okay, and use that to um, send send that to the large language model. So, but the first thing is we will do the RAG prompt. In the RAG prompt, we can um, just do this and something like yeah. So I think this is kind of similar to what we used before. We are helpful assistant provide answers based on the context provided. Use the context to answer the user's questions. The context doesn't contain the answer, respond with I don't know. Okay. Now that is okay. User's question. So can say user's question, and then we will just pass it in as user query. Um, well, this won't work. We need to, yeah, we'll just keep it as a placeholder, and then context, retrieved context. So this retrieved context is actually going to be a joining all of the maybe the top K entries that you have gotten, and then you pass it in. So we can then do something like um, okay, so retrieve chunks comes from retrieve from pinecone. So these are the chunks that match. You can then use this map to take all of the content, because remember, when we retrieve, we are going to get the metadata, which is the metadata that I had added in here, metadata.content. So we're going to get the metadata content, we'll join it, and that gives you the context. Then you will then basically prompt maybe a large language model. Okay, so you replace user query with the query, replace the context with the context, then you will do client. So here, let's make we will use a client, an OpenAI client. So let me, right. And similarly, I would also create a client right above here. I guess it makes sense to um, create a client right above here. Or let me call it LLM. LLM client. Okay. And we can then generate from here. Client dot I'll prefer to do LLM clients dot models dot um, no, not models, chat dot completions dot um, okay. Okay, this is the API. These things change so much that I sometimes I forget. Okay, so this is standard OpenAI. You can specify the model, and the model I will take it from process.env. Right. So we have GPT mini, but I'm going to use well, we can just go with that. And then messages. Yeah. Um, I won't do max token or anything like that. Okay. So we get our responses and then we get the content. I don't know if it fails. Okay. So that's an interesting twist. I was not able to get information. Okay. And then we can catch and log if there is any error. Okay. So we have the full gamut of things that we need. So let's now do um let's assume that we are doing this from a well let's just do it from here. We could also do it so that it's like a command prompt. So we use arguments and all of that, but we don't have enough time for because we still have a lot of stuff to do. So let's just run it. And what we do is basically try a few questions. Now, the first thing is that we have to do an ingestion because we'll first of all run ingestion. Okay. So to run ingestion, we'll run the the whole Okay, so first of all, run ingestion of the document. So the first thing is we will we don't need a separate function for that. So we'll just run paragraph chunking, and then we'll just run paragraph chunking. Then we'll get the chunks from paragraph chunking. Then we'll embed the chunks. Okay, that's all. And then we'll start embedding in Pinecone. So it's 3 steps. Well, maybe we can put that in a method. That's still okay, uh, I guess. So I'll go with that idea. And then we will just run ingestion. Okay, so we're using so after ingestion is complete, since we are using async, then we can run a simple query. Normally, if I wasn't doing a flat file like this, we could use async await, or do um we could do something like async async user query. So we'll run the ingestion in here. Hold on. Yeah, let's just do it this way. So um okay, what is the main topic of the document? So what this does is we run ingestion first. When the ingestion is done in this then section, then we will run a simple query, which is this, right? Please, this is not like a perfect example because ideally you should not run this in the then um, callback of this, right? You should run ingestion separately, okay, and then separately you do this. So these two should actually be in an async function, which is what I was trying to do. I think we can do that in an async function. Um, yeah, we can do this in an async function, which will be better so that this run injection will be in an await, and then we can await it. Um, okay, and when that is done, we can then console log it, and then we run a simple query. We could also move this query the into this. So user queries. Okay. So everything now comes together. You pass the user query in, you run the ingestion first. Typically, you don't always run ingestion every time, right? Typically, you should run ingestion separately. Or when the ingestion cycle is not dependent on the query cycle. So this is not a very good example of how that should be. Typically, you should run ingestion separately. As a matter of fact, that's what we should do. But it's not when you want to do the query that you run the ingestion because ingestion takes a long time. You know, it's a large number of documents. But this is just for demo purposes. And because this is async stuff, I can't separate them, right? Alternatively, I could run ingestion in a separate function call and then use a timer or something and then run a query separately. But be that as it may, let's continue. So we will run ingestion. After the ingestion is completed, then we'll run the query. So the query is run by simply calling um, embed chunks. So again, let's separate this so we can see. So we call embed chunks. And then we now um, yeah, so all of this is not really needed now. If the chunks, yeah, so embed chunks, it will definitely be greater than zero. So this is not needed. We'll now do retrieval. So the steps are, this is a query section. The query comes in, since it is a single string, we make it into a list and we pass into embed chunks, which will now give us the chunks. Um, it's actually the embeddings that you get, not the chunks. So you get the embeddings, and then from the embeddings, you will then retrieve from Pinecone based on that. And you are really just getting the first embedding. As a matter of fact, we could actually just destructure this. We don't need to, we could actually just destructure this. So, and this becomes embedding, just a single embedding. And you pass that single embedding, specify the index name, which I'll replace this very soon. And we use top K of 3. Then we now have the chunks that match the embedding for this particular question. And then we take those chunks, those retrieved chunks, and we pass it along with the user query to the large language model that will generate the response, which we already did here. So of course, each of these functions will have to test each of them separately, and we'll come to that. And then once you get that response, you can then uh, and I think we can just keep all of this in a single try catch, and that should be okay. All right. We just put all of them in a single try error block. And yeah, so that's a full implementation. Then we can run main and we can specify any other user query we want. So I can, um, let's call it RAG. So we can do another one. Um, who coined the name artificial intelligence and in what year? Okay, so we'll run this and we'll debug it because there are a bunch of type matching errors here, which we'll need to fix. Of course, I need to get the additional variables, the index name. I need to get the index name. I need to get the file path. File path is simply text file dot txt. Chunk size, we can go with 5,000 because here chunk size, we are actually using the length, the number of characters, not the number of tokens. Characters are far more than tokens. Tokens are like words, but characters are like letters. So if you look at our chunking section, when we were comparing it, we're comparing the length. We're comparing the length, and this is what happens when you do this kind of naive chunking. We're comparing the length of you know, the entire thing, and the length is in characters, not in tokens or words. So we can take a higher value. All right. So let's start and see if we can debug a few things. The first thing I want to do is to just, before I run main, the rag main itself, I want to first of all confirm now my Node.js has been updated to version 24. So I can directly run the TypeScript file. I don't need to transpile it or anything. So the first thing I want to do is to confirm that all my um, .env variables are in. So I'm going to do that um, in a second. Okay, so let's see how we can do that. I'm doing it somehow in. Okay, so I have OpenAI API key. I have um I'm going to use Open Router and I'm going to use um so I'm going to use a model. For example, I'm going to use the one I usually use in Nemotron. Then I'm going to get a pinecone key. So while that is coming together, I will come back and I'll test run this because of the time constraint. I'll go back to the slides so that we will see. We've just done this with the Nave-RAG JavaScript. It's very simple, even though you have to know what you're doing. And while I'm setting up the other things, I want to quickly run through how to do the same thing with LangChain. With LangChain, it things get much easier to do because a lot of the things that we just wrote out on our own, LangChain already has classes and functions and all kinds of things, which make it easier for you to do. So let's take a look at how to do this using LangChain. After that, we will come back and I'll rerun this, and then I'll also do a LangChain implementation that we can see the difference. So with LangChain, you have an additional um, step, which we actually did it when we were doing the naive rag. The only thing is that we did it without thinking too much about it. We did it without considering too much. Um, it was a naive rag. It was a naive data type. It was basically text, a simple text file. So a simple text file is not a problem when you start talking about things like um, you know, loading the file. But in real life, we don't just deal with text files in real life. We deal with all sorts of file formats, which we have already seen. So the good news is that LangChain provides a lot of tools, basically, that help us to do that. So LangChain provides what we call loaders. And apart from LangChain, there are a bunch of other um, providers, other libraries. If you go check on GitHub that also do loaders. So it becomes easy for you to access different types of file formats. We could actually have used a PDF loader on our own, without using LangChain. But there are actually other, libraries that you could use, for example, to load a PDF. But you have to do a lot of work on your own. So LangChain solves that problem by giving us loaders, and we'll look at those. So the first step you are going to do is to read the document, which is what the loader does. So that's the first component that LangChain provides. Then it provides splitters. Splitters do the chunking that we just talked about. And while we took a few minutes to write a simple paragraph-based chunker, with LangChain, you effectively um, just get all of that for free. So, and they have a lot of different chunkers, different strategies. We'll look at that as well. Then embedding. Embedding is still done the same way. The only thing is that you now have a unified interface for embedding. You don't need to try to remember, like I was trying to remember, how do I, call the Hugging Face or any other API. LangChain provides a unified interface for you to access different embedding models and embedding providers for you to do the embedding. Same thing with vector store. LangChain also provides a unified interface for you to access all the different vector stores. So you don't need to remember for Pinecone, this is how I will do the, uh, how I would save the embeddings. I don't need to remember all of the different interfaces. It's good to remember though, right? If you need to do specific stuff. But LangChain provides a unified interface. So it's easy for you, whether you are dealing with Pinecone, you're dealing with Fies, with Chroma, with Qdrant and all the rest of them. It's the same way. But if you are dealing with their SDKs directly, each of them has a different interface. So that's another value that LangChain brings. Then LangChain also has an abstraction called a retriever, which doesn't really exist anywhere. A retriever is effectively a a vector. Think of it as something that allows you to search embedding space or search with similarity search or any of the methods for search, right? So, and the interesting thing with LangChain retrievers is retrievers can be made from anything. So you can make a retriever from a vector store. Yes, you can make a retriever from a vector store that allows you to do similarity search on what is in that vector store. You can make a retriever from a website, right? So it allows you to do a similarity search based on the content of that website. That's how powerful the retriever um, concept is, right? And we'll look at it in more detail. And then, of course, the LLM, which we've already looked at, chat this, chat that you would then use the 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 response that you get or the results that you get from retriever, you use it to augment the LLM. So let's start with document ingestion. You have loaders for different types of file formats. Okay. For PDFs, LangChain gives you a PyPDF loader, and it's called PyPDF loader because this is on the Python side, by the way. It's because there is a Python PDF library called PyPDF. So this is just very simple. Then it also has a text loader that allows you to load simple text files. It has a CSV loader that allows you to load CSV files, comma separated value files, which are files that are in kind of a, spreadsheet format. Then it also has a JSON loader that allows you to load JSON files. A web-based loader, which allows you to load content from a website. Basically, you're reading the website, you're reading the content from the website. So they also have that. They have a directory loader that allows you to load everything in a particular folder or directory. So the loaders give you a lot of power and flexibility, right? In LangChain version 1, all of these have been moved into the LangChain community namespace, right? for Python. For TypeScript, JavaScript, it's also still in the LangChain community, but you really need to go check on their site to know exactly where to get those things. The other interesting thing that LangChain provides is, along with the loader, the different loaders, it provides a single abstraction called a document. So a document is anything that the loader loads, it loads into this format called document that has page content and metadata. That's the structure. So it's easy, irrespective of where you load it from or the format you load it from. The result will always be the same thing. It's a unified format called the document. And so every loader will load a single document, but the directory loader will load multiple documents. And this is how you can use a directory loader. You specify the directory you want to load. Then there's what we call a glob. A glob is a kind of it's like a regular expression, but it's not really a regular expression. It's just a wildcard pattern format that you use to specify files that should match. So in this case, what this means is a double star means any directory of any depth, and the single star means a single file name. So what this will do is it will load files that match any specific, files that match the .pdf extension. Okay. And once you create a loader, then you can just call loader.load. And yeah, so the document loaders from LangChain, the benefits, they allow you to do bulk ingestion. You can actually ingest a lot of files at once, right? They support large repositories, basically large document repositories, and it's easy for you to automate. So the typical sources that you would use to load or you would point the loaders at would be knowledge bases, company documentation, research papers, and manuals. So after you load, the next step, like we have seen, is splitting. So for splitting, you use the text splitter. So LangChain has a sub package called LangChain text splitters. In version 1, all of the splitters have been moved there. And you have different splitters. We'll look at a few of them shortly. So you have the recursive character text splitter. You have you have the um you have you have what as character text splitters, token based splitter, so we'll see all of that. But the recursive character text splitter is the one that is used most often. And it typically is your starting point because it looks at the structure of the file. It looks at the structure of the file, and then it kind of if it can split it into the largest chunks, which are paragraphs, it will do that. But if the paragraph is too big to fit into the chunk size, then it will go to the next smaller logical structure or semantic structure, which is the sentence. So the benefit of that is it keeps going until it gets to the largest semantic structure that can fit into the chunk size that is specified, right? It also allows for chunk overlap. So the benefit of using a recursive character text splitter is that it preserves semantics and it can handle documents of different types. So it's a good choice for you to use as a default because it can handle most documents um, easily without having too many challenges, right? Okay. Then the other types of splitters that we have the character text splitter. This just does fixed size splitting based on fixed size chunks. Okay, and this is the one we talked about earlier. It can sometimes chunk in the middle of meaningful words, sentences, and so on. So one needs to be quite careful about that. Then we also have others. We have the token text splitter. So in this one, it just counts tokens, right? It uses token counts instead of character counts. The character text splitter uses character counts to determine the chunk size. So when you say 500 as a chunk size, you're actually saying 500 characters. But for token text splitter, when you say chunk size 500, you're actually talking about 500 tokens. And so remember I said um for large language models count tokens, not characters. So if you want to kind of match what large language models specify, their context window size and all of that, it's better to use a token text splitter to count, right? Then we also have a markdown header text splitter. This is very good for chunking markdown files because if not, you tend to lose this hierarchical, structure of markdown files. The markdown header text splitter will chunk based on markdown headers, basically. So, if there's documentation that is expressed as markdown or anything like that, it's always a good idea to use this particular type of splitter. Right. Then after that, you do embeddings. So with embeddings, you have embedding, um, this kind of embedding abstraction, basically. So if you want to use OpenAI embeddings, for example, you can get LangChain OpenAI, right? OpenAI embeddings from LangChain OpenAI, or you can have Hugging Face embeddings from LangChain Hugging Face. So like I said, the embedding models now have a kind of unified interface, right? It has a unified interface that allows for a unified interface that allows for you to just address or to use different embeddings without having to use different syntax, right? So with LangChain, once you have defined an embedding, then you just run embed query to embed the query, right? And this is what you use to generate vectors. You can use lists as well and others. Okay, so the other thing that LangChain also provides is vector databases, the abstraction for accessing vector databases, right? Um, so this is how you do that. Basically, you can import a vector database. Each of the vector databases has, like, for example, LangChain Chroma has a class that you can then use to create a vector store. So you create a vector store type, right? And then when you create that vector store type, then you specify the documents, which typically should be documents that you have already chunked using a previous text splitter. And then you can specify the embeddings, which again, you created. The embeddings here refer to the embedding class that you have created, right? That will be used to embed the chunks, right? So these embeddings here doesn't refer to embeddings that have been, or doesn't refer to chunks that have been embedded. It rather refers to the class that will do the embedding post-chunking. So typically what happens in a vector store, if you look at this particular workflow, is that you have a chunk, that chunk inside here, right? That chunk goes through the embedding, and then you have a vector, and then that gets stored in whatever vector store that you created. So effectively, the vector store becomes a searchable knowledge base. Okay, so after that, then you have retrievers. So a retriever is a, a construct that effectively allows you to find the most relevant chunks. And retrievers are built in such a way that you can chain it. So a retriever is a runnable, just like the other things that are runnables in LangChain. Remember that the LLM is runnable, the prompt is runnable, right? And a bunch of other things. So a retriever is runnable as well. So that means you can take a retriever and put it into a chain. So you can get a retriever from a vector store after you have created the vector store in this manner, right? You can you can then create a retriever. You can get the vector store as a retriever. And then to use a retriever, you use invoke. So you call invoke and you pass in the question or query. And what the retriever will return to you is actually a list of documents in that vector store, or a list of chunks, I should say, in that vector store that matches that. Of course, remember that all of these LangChain has provided a document abstraction. So that's what you will get when you call retriever. So inside the retriever, what's actually happening is that you have a question, right? Then after the question, the retriever will generate an embedding for that question, right? Remember when you created a vector store, you had provided an embedding. So the same embedding that you provided, the same embedding class that you provided when you were generating or when you were creating a vector store is that same embedding that the retriever will use to generate the vector for this user query, right? And then carry out similarity search still within the vector store and return your top K chunks that match. So the docs you are getting are actually chunks. Similarly, when we're talking about documents, one thing I forgot to mention is that this document abstraction, right, are actually chunks, right? So you could look at them that way. So that's the summary of all the tools that LangChain provides. But in addition to that, LangChain also provides what we call retrieval strategies. So your retrieval, you can decide how you want to do it. One of them is which search method you want to use, right? Um, you can also decide how many of the matching vectors or embeddings or matching chunks in the vector store that you want to retrieve. So that's always the K number. That's why we call it top K, right? So that will be passed in as search KW args. Then there is also something called MMR, the max marginal relevance, right? Which allows you to balance relevance with diversity, right? So you can specify search type MMR. This this allows you or this helps you to avoid duplicated chunks because what it means is that if the chunks are similar or duplicate, there is no need to retrieve, the same thing several times. So what you do is retrieve, you know, um, kind of unique, um, you know, pieces of or chunks, that match the thing. Then there's also metadata filtering. So metadata filtering allows you to look at not just the semantic meaning, which is what you get when you are filtering by the vector embeddings, right? But also additional things. These metadata help for you to limit the search to what matters. So for example, if your documents, if you only want to search in documents for either HR or for medical, then you can use metadata to specify where you limit it to. Metadata is also what you use to limit access, to the results. Limit the access to only those who are authorized to access it. So for example, if the data is private, right, you would have to um use some kind of you know system, right, to add who and who is supposed to have access. For example, you could decide, let's say people in a workspace, or people that are in a particular work group or in a particular channel, right? So those are the things that you have to add to the metadata when you are ingesting the documents, okay? So that when it is time to retrieve, you can also still retrieve using and filter using those same metadata. So it's something to think about. Um, yeah, then there is advanced retrieval. So advanced retrieval is where you can use multi-query. That's one way. Multi-query retrieval is where you have the LLM generating multiple search queries. Okay. So if the user passes in a prompt or a question, you ask an LLM to come up with five, for example, five different variants of that same question. The reason for that is to have diversity when you are generating the embeddings so that it can match more chunks, right? If for some reason maybe the user's question was not broad enough or clear enough or detailed enough, there may be some missing aspects. So when you are now converting it to the chunks that you use, you find that it becomes very difficult because, or not difficult, but it doesn't match. It may miss some key elements or some key chunks that would have contributed to that answer. In fact, if you remember last time when I did the naive RAG with Python, you remember that it actually missed some chunks that would have helped to answer the question. So what this does is it broadens the footprint of the search. It broadens the semantic, space, right? So that you search each and then you merge the results. So that improves the recall. And this is a very good strategy that you would use in an enterprise RAG, for example, to make sure that um, maybe a user's query, if it is too narrow, does not miss some key information. Then we have the parent document retrieval. So in this case, the strategy starts from ingestion. When you are ingesting, you actually keep track of the parents of the chunks. So not only are you chunking a document to smaller chunks, but in the metadata for each chunk, you still have a reference, maybe either the page number or the section number or the link or something, some kind of reference to the larger parent document or parent section, the larger parent, maybe even the whole page from which that chunk was taken. You maintain a reference to that in the small chunk. So yes, you save the small chunk along with other things in your data vector database. But when you are retrieving and that chunk matches, you retrieve not only that small chunk, but the entire page, the entire parent of that chunk. So that is also a very good strategy because it helps you to get the broader context from which a small chunk came. It gives you richer context. So that is more helpful. This is really important where you have a lot of text that is mixed with other kinds of media, for example, with tables, with images, and so on, right? With references. So you may miss the image, right? Let's say you have text that was a caption for an image and you miss the image when you were chunking. Of course, it's an image, right? But when you now pull the text and you pull all the surrounding context, the parent section, then you also be able to pull the image and other things, tables and so on. So that makes it better. So that's parent document retrieval. Then we also have contextual compression. So in this one, the documents that are retrieved, you still filter out irrelevant text from it so that when you want to send that retrieved context, you send a compressed version. The benefit of this is it reduces token usage. So a good example is if you were to even do this parent retrieval or parent document retrieval approach, you might find that there's a lot of repeated information and so on. So you can then filter out irrelevant text and send a compressed context. So that helps to kind of give your large language model a much better context without consuming too many tokens. So remember, everything comes down to tokens and context window. Okay, so those are some of the additional advanced methods that you would use for your RAG, um, you know, advanced RAG. And here are best practices to follow. In ingestion, always clean documents before indexing. Cleaning documents help to remove noise and remove useless information and data. Always remove duplicates because duplicate is just going to take up space and confuse your retrieval. So removing duplicates is a good practice. Preserve metadata. Metadata could include section names, document names, the section from which that chunk came from, references, and a whole lot of information. That metadata is very, very useful. Then, when it gets to chunking, always start with recursive chunking because recursive chunking is very flexible and can handle almost any kind of data or documents content. You only may go to other specialized type of chunking if recursive won't work. For example, maybe if you have images, a lot of images or something, then you have to figure out, come up with a different strategy. Use overlap as much as possible, 10 to 20% overlap, 10 to 20% of the chunk size. The overlap is going to help because overlap allows continuity between the chunks so that a chunk can can connect to the previous chunk before it, right? So that improves the context when you do retrieval. Always test your chunk sizes experimentally. In other words, allow so your chunk size you can play around with it, adjust it, right? So that means you should not hard code it into your into your app, right? It should be some kind of environment variable or some other variable or constant that you can easily change in one single place and try it out. So you try different chunk sizes and see which one works best. For embeddings, use modern embedding models. Modern embedding models are more meaningful. The resolution is better. They have better understanding and nuance. So they are more likely to be accurate and they will not mix up ideas or semantic meanings. Always re-embed after major content changes. If somebody updates the documents get updated, modified in any way, you have to rerun the ingestion pipeline to do re-embedding again. Okay. So always re-embed after major content changes. Benchmark your retrieval performance. Always benchmark retrieval. It is very helpful because you know if your retrieval is fast enough, if it is accurate enough, and if it is giving responses that you want. In fact, there is evals as well that you can use to check how well it is doing. So always do that. Then when it comes to retrieval, tune your top K, right? All this while we have been using default of 3 or sometimes 5, but that's not necessarily the best value. Right, you can use other values. And just like we talked about with chunk size and others, you can tune your top K, you can adjust the values to see which one works best. Um, in fact, there may be some complex approaches where you can adjust the top K based on the um, type of um, data or type of document and on the type of use case. So for some use cases, you may use higher values. For some, you may use lower values. Use metadata filtering. Metadata filtering is always good because it allows you to restrict and scope access to the document, right? So if not, you may have, if you are doing if you're implementing RAG in an enterprise environment, you find that people who are not what people will be seeing things they're not supposed to see or they're not supposed to have access to see because you didn't do metadata filtering. So it's very, very important to have the right metadata when you are ingesting and then to filter adequately when you are retrieving. Okay. Then consider hybrid retrieval. We'll talk about hybrid retrieval later. Hybrid retrieval is retrieval where you use agentic methods as well, right? So we'll look at more detail of hybrid retrieval later on. Yeah, so these are other things to also look at. Um, kind of the summary of everything that we have said. Um, the document chunking is the foundation of RAG, right? It's the foundation of RAG. So you basically it's also the foundation of the quality of retrieval, right? So if you don't do good chunking, you'll not get good retrieval. This is very, very important. Then semantic chunking also outperforms fixed size. Fixed size is not really good. It's bad actually because you don't have any control over where in your documents that your chunk ends and starts. It's basically you're just cutting things at in the middle of sentences and so on. Metadata greatly improves retrieval. So these are the three key things to take away. For embeddings, embeddings will convert meaning into vectors, yeah, and it drives semantic search. It's embeddings that give RAG the power that it has to essentially allow your large language model to have more meaningful context for it to respond and you know to respond to user queries. Vector databases enable the fast similarity search and they allow the knowledge retrieval to scale. They are very highly optimized, very fast, very powerful, and they can scale. Retrievers are essentially a LangChain abstraction that allows you to just connect the user's query directly to the results, the matching chunks. So you don't need to do a lot of work in between. You just use retrievers. So, and it's a very useful LangChain um, concept. So at the end of the day, LangChain provides that complete framework for you to build a production grade RAG pipeline, starting with the loaders, then the splitters, embeddings, vector stores, retrievers, and then the large language model orchestration. So we are going to do a bit of hands-on with this, right? And I'm just going to show you how to do this quickly with um, uh, the sample code here, right? And I'll try to explain it as well. This time around, we are using Chroma. So we used Pinecone before, but we'll use Chroma this time. And it's not really that different. So let's get to it and see how fast we can do this. So I'm going to do this again on a Jupyter notebook. So on Colab. Okay, so the first thing we will do here is we'll get let's say we want to do a PDF, right? We can try a PDF and then we can also try a web-based RAG from a web. So for PDF, you can use the LangChain's PyPDF loader. So PyPDF loader You get it from the LangChain community, and it's still the same thing. You will still get it from LangChain community if you're using JavaScript. So I'll later on I'll share a JavaScript sample where I am doing basically the same thing, but using JavaScript. Okay. So let me test this just to be sure that we are good. Okay. Well, then LangChain text splitters. So this is also another um it is now standalone. Before it was part of LangChain, but it is now a standalone module or library that allows you to bring in, and they have a lot of text splitters. If you actually check, you can check their documentation. So I need to install LangChain community here. It's not, I just wanted to be sure. I just want to be sure. Of course, this requires LangChain as well, but LangChain is already built into this. So while that is installing, I also need to install the LangChain text splitters as well. So I might as well just install that LangChain text splitters. Then we'll as well install the LangChain OpenAI and LangChain. Um, yeah, we'll go with that. Okay, we'll LangChain Hugging Face. So we'll also do that because we want to use the Hugging Face. We want to use the Hugging Face embedding. So we will do LangChain Hugging Face as well. Um, yeah, I think those that should be all. Um, oh yeah, we will need Chroma for the Chroma database. So we'll also have LangChain Chroma. So this will also install the dependent vendor module because if you install LangChain Chroma, it still needs Chroma, right? If you install LangChain Hugging Face, still needs Hugging Face inference client. If you install LangChain or OpenAI, also still needs OpenAI, but those will be installed along with it. So if you even look at it, for example, LangChain Hugging Face, let me just show you. You'll see that when it installed LangChain ChromaDB also got installed along with it, and then a whole bunch of other things. So the dependencies get installed that way. Okay. Um, Now I can rerun this, and this should now be able to pull in all of that. So I'm going to also pull in everything else as well. The text splitters, we'll bring in the recursive character text splitter. We'll get the OpenAI, we'll get the Chroma, we'll get the Hugging Face embeddings. And then I think that's all we need. Okay. So it becomes very easy to get stuff now. I can get a loader, I get a PyPDF loader, and then we specify a PDF name, right? So just call it my PDF file dot PDF. And I'll have to upload that here. So I'm going to look for a PDF file, or better yet, I will go to the, again, that AI, artificial intelligence Wikipedia article. I'm going to print it to PDF and then upload it into this location. So let's do that. Okay, so this is a PDF. I'll just print it off somewhere, and okay, and I will upload it once it has completed writing. So we have a PDF file, and I will even run it. So, but first, let's create the loader. Right, I do need to have the file first. So let me upload this file. So I have the file. It's coming up. So you create a loader, and the loader is tied to a single file, right? That's the interesting thing. You have a loader is tied to a single file. Now I can then call on loader.load. I would like us to inspect what happens, what is inside this. Okay, the PDF file has not yet fully loaded. Um, or maybe there's an error. Seems there's an error. Oh, okay. So the PDF file, it seems, did not write. Um, so I'm going to try again. Yeah, so let's use save as PDF. Probably will do better. Okay, so while that is going on, I'll just keep typing. So you load the document. We're going to come and inspect the document after loading it. Then we create a splitter. So the splitter we create, of course, is a recursive character text splitter. Chunk size. Yeah, we'll just go with this. Okay, so right. So I did not first import this, so I think I need to import this again. Um, right. And then, okay. So after creating the splitter, so you can see all the steps are there, but Because LangChain has done all of the work for us under the hood, it becomes really easy. Right now, um, loading was still a one line thing before, right? But splitting was a whole function we had to write. Now we are just calling a function or a class that LangChain provides. And then we just get the chunks. And we'll get the chunks by calling on the splitter. We use split documents. Splitters have different functions. So you have split. If you actually look at this, right, it gives you a lot of create documents where you can create from a list of text, a list of strings. You can actually do that. You can do from language, right? You can do split documents where you specify the documents that you want to split. This one will be for documents that are loaded via loaders. So you see that there are at least two ways. The first way is to use create documents where it creates the documents from a list of strings or text. Or you have split documents where it splits documents that have already been created by a loader. Or you use split text where it splits a single string of text. And then you have transform documents. So let's go with this one because we already have created documents. And that's it. We can now look at these chunks. Okay, we haven't created this yet, so I need to go back and see if our um, PDF document saves properly. It wasn't saving properly before. Okay, let's see if we can upload it again. So it looked like this time it was successful. So it was successful. So you see AI history. So let's change this now to AI history. And okay, AI history PDF. AI history PDF. Right. So yeah, so one thing I forgot, the PyPDF package. I was expecting it should have been installed along with LangChain's document loader, but it is not. So we still have to install it separately. Or we could have installed it along with that. We need to install PyPDF. Yeah. So it is kind of a runtime requirement. It's only at the point when you want to use it, then it will ask for it. So now I have installed it and you can see it has loaded or it's loading. You can now go check the docs. So you see what is in docs. It's basically a list of LangChain document objects and the content in them is the entire content of this PDF document that we just uploaded. So that is the content of the RAG. You can see it's a document object and it's a list of document objects. And you see there's a lot of metadata, right? Along with it, including total pages and all of that. Then you have the page content, right? Which contains that. So that matches the schema that we saw the other time. The entire page content is there. So um, now with all the references and everything. So that's the docs. We've done a recursive character text splitter. We now take the text splitter and we split it into chunks. So now let's look at the chunks. All right. If you look at the chunks, you see that the chunks are also going to be LangChain documents. So the original document that was loaded is a LangChain document, and the chunks are also LangChain documents. So it kind of forms a unified interface, right, for you to see. It also allows the hierarchical relationships to be seen. So you see, after chunking, we still have each of the chunks is still a document, right? And it still has metadata as well. Um, and then it also has content. So it also has page content, right? But this time around, the page content is now shorter because it is chunked. So you see the page content for this first document is a small chunk that is based on the chunk size that we gave, which was 1,000 characters. And you can even see total page is 51. This is the original the metadata pointing to the original document. So that's why we're saying metadata is very important to create a relationship with the original document. So that's the first chunk. If you actually look at it, you will see that there is another document here, which is the second chunk, right? And it also tells you the metadata contains other things. Then you still see the page content. If you even take notes, you see that here is a bit of overlap, right? Um, you see applications of AI in different sectors. You see irrigation, fertilization. You also see that application of AI in several different sectors, and you see it goes to irrigation. So this is an overlap, which is based on the overlap that we specified. We specified overlap of 200, and 200 is 20% of 1,000. So that fits into what we want. So that's the second chunk. See, the chunks are smaller. And then there's a third chunk here as well, right? Still starting with a document. So each chunk is also a document. And then you also have another chunk. So these are all the chunks. If you check the length, you can check the length of the original docs and the length of the original chunks and see the difference. So the length of the docs and then the length of the chunks. So the original document is 51. There are 51 items, 51 documents basically, but you have 235 chunks. So the way the PDF chunk PDF document loader did was it loaded each page as a separate document. That's why you have 51 of them, right? Because if you look at it, this document actually has 51 pages. It actually has 51 pages. You see that information here where it is originally mentioned as having total pages 51. So each page was loaded as a separate document. But when we pass it through the chunker, the text the splitter, recursive character text splitter, it's split at 51 pages, 51 documents into 235 chunks. Okay. So then the next thing is we will now do embeddings. So to do embeddings, we are going to use Hugging Face embeddings, right? We've already pulled in Hugging Face embeddings here. So we don't need to try to remember how Hugging Face embeddings works. The only thing is, of course, we need to remember to put in the um the key, the HK token, right? It's going to ask for it at this point, if I haven't done already. The only thing is, yeah, this is using sentence transformers, so it's actually going to download the sentence transformers. So the thing is, yeah, this typically does not Hugging Face does not bother about tokens for public models. It still allows you to access them. But it still asks you to create tokens, if you need. to have access to the closed models that are not in public. But yeah, this will work for us. So we are using sentence transformer, and maybe it's likely the all mini LM that is the default. So we have the embeddings. So you can see the components are coming together. We have the document, we have the splitter. We split the document with the splitter into chunks. And now we now have the embeddings. Each of these is single line. Now we create a vector store. So we create a vector store. If you remember how we did with Pinecone, we had to do an index and all of that. We could also do the same thing with Pinecone here, but it becomes very easy. So with a vector store, you can use from documents to pull from LangChain's built-in documents. You could either do it from the original documents, which are still a list of documents, or you can do from chunks. But the chunks are better because the chunks are smaller sized. So here you specify the documents, right? I didn't have to do the embedding, do the embedding translation. The LangChain, does that for us, right? This the Chroma LangChain integration, right? Does that for us. All I need to do is provide the chunks that I want to embed and store, and then I specify the embeddings. And then for Chroma, there's this third thing I have to specify, which is a persists directory. If I was using Pinecone, I would have to specify the Pinecone API key as a third argument, because if not, I will not be able to connect to Pinecone. So you see how it will be much easier. As a matter of fact, we can even, we can run this, right? This is if I want to store in a local directory. So you can see this is actually ingesting these documents right now. From documents, does ingestion straight up. So that whole thing that we wrote about ingestion is happening here. So that simplifies things a lot for us. And the beauty of this is that you can turn this into a pipeline, a chain. So anytime there's an update, you get a new chunk, you get documents, you reload it, you resplit it, you rechunk it, and you run from documents again. Okay. And then you can offset. Well, from documents actually does offset as well. While this is running, we could also do the same thing with Pinecone, right? With Pinecone, we could do pip install LangChain, um, LangChain Pinecone. And I think we'll still need to install Pinecone, but LangChain might actually install Pinecone along with it. So you see, this is taking a bit of time because it's ingesting 235 document chunks. It's calling the embedding endpoint. It's calling the embedding model, the Hugging Face embedding model. It's embedding. Then the vectors, it's essentially creating entries in the Chroma, and then it is installing it, or it's offsetting it, right? Unfortunately, this one will not run until this is done, but we can do the same thing here. So we could do a Pinecone vector store, and that would be okay. We'd need to first of all import from Pinecone, from LangChain Pinecone. We import Pinecone, right? And then we just do the same thing here, Pinecone from documents. So you see how much easier it is here, right? We'll even specify the index name, okay? And then, of course, the API, we can create a .env. We'll need to create .env where we can put in the API keys, right? So, so while this is ingesting, I am going to set up the other things. I need to set up the Gemini. I'm going to use Gemini for the LLM. Well, I could use OpenRouter as well, or OpenAI. So there's a whole bunch of flexibility. It becomes much easier, right? Okay. So I'm going to set up Gemini API key. I'm also going to set up Pine. Wanted to use Pinecone, we would have to do a Pinecone API key as well. And then we'll have to do oh yeah, so let's just have those for now. Um so you can see it's done chunking, right? I'm not going to restart the session because that would just means I have to start everything all over again. So I'll just continue as it is. Um so this also works, right? And it will take about the same time because but let's anyway it will not because we have not set up Pinecone API key. Is going to complain about Pinecone API key. So if you want to do that then but I just wanted to demonstrate that you can do exactly the same thing with Pinecone, but you specify your Pinecone API key as the environment variable. And then of course remember the index name here, you put in the index name. And it's as simple as that. It's now using Pinecone rather than using the chroma. So you even see where we specify DB, the persist directory, the chroma directory DB. So you see the chroma database is in here, even though it's not showing up. Probably need to refresh it or something. Okay, so we have, I want to show now that after doing that, you can then check the vector store we just created. And you see, yeah, it's just a, you can then do stuff with this vector store. So for example, um, if in a RAG workflow, right, you really only need to just get a retriever. That's the power of a retriever. I can then get a retriever. I don't need to do anything else, right? It's only if I want to use a vector store for something else, then I can go do all of that. But with LangChain, you just get a retriever from the vector store, right? As retriever, and you get a retriever, okay? And the retriever is there's nothing special, but it contains all the magic, all the code that you need, all the code that we wrote for search. You can see it's a vector store retriever, it's chroma vector store with Hugging Face embedding. That's what it is. And then it holds a reference to the vector store and the embedding. And then you can pass in the search keyword args if you want to. So if you want to use this retriever, you can then do results, right? Is retriever dot invoke. Get relevant document is another, we'll look at that, but get relevant document is going to essentially give you the matches. But invoke is going to, well, invoke is also going to get relevant documents. It's the same thing. So if you run this, you see that you're going to get the documents that match the question, what is AI? Or we can even ask our own question, who coined the term AI? Okay. And we didn't specify top K, right? So it's going to go with a default of 5. And you'll see that there are 5 documents that have been retrieved here. This is the first one. And then this is the second one. And so on. Third one. Um, this is the third one up to here. This is the fourth one up to here. And there should be 5. So I think I may have skipped one. Unless the top K was 4. But we can actually check it we can just check the length of the results, and that will tell us, okay, it's 4. So it actually, the top key was 4. Right. So, or maybe couldn't find anything more. We can also check the page content and we would see um, a whole lot of stuff. Now, that's it. You've gotten the retriever. The retriever gives you the results. The next thing is to take the results of this and add it as a context to your um, to your LLM call. So you can do a prompt. Remember, a retriever is a runnable, so you can use it as part of your chain. So we are now going to use a standard lang chain chaining approach. So the first thing we will do is we need to create a prompt. So of course, to create a prompt, we can create a prompt. We can make a prompt template file, or we can make a chat prompt template. So let's make a chat prompt template. So from LangChain, LangChain dot prompt, LangChain core prompts, import chat prompt template. So we'll get a chat prompt template, and then we will make a simple prompt and chat prompt template from messages. You can then put this. You can put well, okay, let's just use a standard prompt template. Either can be used, I guess, and pass it to the LLM. So just for simplification purposes, prompt templates, I need to import this first. So prompt template from um, template. So you create it from a template, and this template is basically just the string template where we can pass in um, so it's kind of the same thing, right? And then you would have user query. User query, we'll use a placeholder, so remember, and then additional context. You also use a placeholder context. So we create that, and after creating that, you now have a prompt, you have a retriever. So you can then chain the prompt to the retriever and um, chain it to the LLM. You can chain the prompt to the retriever to the LLM. Even though the retriever, you would need to use a lambda to combine it to make the context. So the most kind of easy to understand way to do it would be um you would first invoke. So we've created a retriever based on the question that was asked. Okay, the retriever has given us results. Okay, we can then take this result and pass it into the prompt as a context. So you can then make a chain like this and say chain equals prompt and LLM. So oh, by the way, you need to create an LLM first. So to create an LLM, let us use a Google Gen AI or Google Gemini, which I already have the API key here. So let's create my Google Gemini. So we'll do from LangChain Google Gen AI import chat Google generative AI. So if this doesn't yet exist, I will have to install it. Yeah, so I have to install this. So I'm going to just install it quickly. Pip install LangChain Google Gen AI. So that gives me the access to the model. And then I bring that in. So this is a runnable. I can then now create a new LLM where I can just say LLM equals chat Google generative AI. I don't need to specify. Okay, I need to specify the uh the 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 key. The API key will be pulled from environment, but I need to specify the model. So I could say model is we can say Gemini 2.5 Flash. So okay. So okay, the environment variable was not loaded, so I need to load it. Um, so from .m import load.m. So I need to load that, and it is now available. Okay, so I now have the LLM. So I just chain the prompt to the LLM, right? And then I can even chain it to a string output parser, which I can get from um, LangChain. Um, I don't think I got that correct, but I'll come back to that. So, so I chain the prompt into the LLM, then I can easily now run the chain.invoke, and we pass in the parameters. So the user query is the same query that we used to generate the that we pass into the retriever who coined the term AI. Then the context will be the results. We can just join the results with a string, right? With new lines, results. Let me double check what results is. So it's a list of LangChain documents. So we could just use a rough approach of um, normally you would do something like results dot or doc dot um, content uh, page content for doc in results. So this is yeah, you could just take this and this is kind of the combines all of the page content. Then we can just take this and use this to put it in there. So we're not just putting the results. And then we invoke. So Retriever has given us this, right? Retriever has given us this, and then we now invoke the large language model. And we pass this into results or response. And then we just have response.text. It says I don't know. So that's interesting. And I wonder why. Um, okay, so something has gone wrong. We probably need to improve on the query. Um, oh, okay. So it's saying I don't know because for some reason that answer is not in the document. So let's try a different set of, we can still take the retriever and invoke. So let's try that now with a different question. We can actually put all of this in a single chain, right? Or in something like this. Yeah, results and then response. You invoke the chain, same query, and then you return the response. So this is just a function. Then we can just call that function get answer. Um, when was the first AI winter recorded? Wow. Okay, that's interesting. So retrieval is probably not that good. Um how many people contributed to AI development? Our our chain is now being a bit wow. Okay. Um Tell me what information you have in the additional context. Right. So, this is me troubleshooting this. Um, so it means our retrieval is not very good because what we have is a lot of citations and references. Um, we can actually test that by passing this same query into the retriever and sorry, retriever.invoke. Let's just invoke the retriever with this query and see what the retriever retrieves. There's a whole lot of, I think it's more of, it's a retrieval problem. And this is exactly what we are talking about when we say you need to check carefully. You need to check carefully. Retrieval is the most important thing. So I have this document and let's see if I'm searching for page content, which is what I really need for this particular one. So you can see that this is references. This is a reference. This is a reference. Page content is NT slash. This is and the dataset shift problem NG daily. So our retrieval is not very good. That is why the large language model is not able to give us a lot of answers. And so that still points to what we say when we say um, the quality of retrieval really matters. So I think I'll leave this as an exercise. The main thing, I think the main reason is that our document had a lot of references at the end. Now let's try another question. Um, when who coined the name Intelligence. Again, the other thing is I think we are just pulling the top four. So again, we have mostly references. So our retrieval is bringing in a lot of references, and that is why um, our large language model somehow is not able to extract um, a lot of information. It's not very useful for the large language model. So we can troubleshoot this, but this is how you implement RAG anyway with LangChain. Now we could improve on this PDF. I could have skipped the references, right? Or we can look for a way to filter out the references or to mark them as references so that they're not part of the document. You'll find that this challenge we just saw now is a real world challenge. That's the kind of challenge you face if you're not careful about retrieval and about ingestion. In fact, that's why one of the best practices was clean your data. And the question would be, should we have added references as part of the data? Should we have done that? Maybe that is what is now kind of corrupting um, the chunks. We have a lot more chunks that have so many references. We probably should have figured out a different way to handle references. So that's it. That's how we do RAG. Unfortunately, we didn't have time to go back and run the JavaScript one. So I'm just going to share the JavaScript so that everyone can run it. And then as well, I will share the JavaScript um, example for this LangChain one that we did, the JavaScript counterpart for it. That's it.